As promised last time, we will prove today Theorem 23, among other things, hopefully, but this one is actually more complicated than it looks. So this one is about this two-element set, or doubleton construction, and it shows you that the order in which you list the elements really does not matter. So where Theorem 22 here, which is one of the problems on your homework, shows you that repetition does not matter. If x and y are the same thing, then listing them both doesn't necessarily give you a set with actually two elements. Theorem 23 shows you that the order in which you list elements does not matter. So here's the exact theorem statement. It's an if-then. So we need to prove that if these two, which I'm calling doubletons, if these two doubletons are equal, then either one thing or another thing. Either it's because the first things match, x with u and y with v, or it's because the outers and the inners match, x with v and y with u. Okay, so I need to start by assuming the hypothesis. Assume the left side of the if-then. So assume this. Then my goal is to prove this or, right? So that means either, if I'm proving an or, then either prove the one side or the other side. So in other words, I need to either prove this or prove this. But this is quite challenging to try to approach it directly that way. It doesn't sound possible. I don't think that this is necessarily true given my assumption. And I don't think that this is necessarily true given my assumption. So I definitely don't expect to be able to just straight up prove this, for example, from where I'm standing now. What might happen is, and what you've probably seen happen before with earlier things, is in this situation, I might somehow get a proof by cases, not based on this or. Remember, this is an or we're trying to prove, not an or that we have, but a proof by cases may be coming out of some excluded middle, some case split that I have yet to think of. And maybe within the individual cases in that proof by cases, I would be able to prove maybe this one in some cases and this one in some other cases. So that suggests that I need to think about in what situations, in what cases would I have the one side versus the other side. Okay, well, let's think. Why would I expect that x might equal u? So let's focus in on x. Why would I expect that, given my assumption, x might maybe equal u, or x might maybe equal v? Why would I expect that at all? Thinking intuitively. Well, these are equal. That's my assumption. When things are equal, axiom 2 here is, or theorem 4 here, would be the way to use that fact. When things are equal, that means anything that holds for one of them holds for the other one. Right? If x equals y, then anything that holds about x also holds about y. So whatever I prove about this side would also be true about that side. So what about this side? What about the equality makes me think that x is either u or it's v? Just focusing on x specifically. It's the fact that I imagine that x is in here as an element. And so if these are to be equal, then x would also be in here. But if you look in here, then there are u and v. That's the intuitive idea. X is in here as a sort of fact that I do need to prove, but I think that's true, that x is in here. And if these are to be equal, then x would be in here then, by axiom 2. And that makes me think that x is either u or v. So that takes a little thinking to come up with an idea like that. But yeah, let's just get started with trying to put the ingredients together. So now my goal is to prove x is in at least the left-hand side. Because then, if I prove that, then by axiom 2, it will be in the right-hand side. So how can I prove x is in doubleton xy? Well, I have no choice but to use the definition of doubleton. So looking here, definition 17, it's this. So doubleton xy is the set of things that are either equal to x or equal to y. So according to axiom 5, what I need to prove is that x is either equal to x or it's equal to y. By axiom 5, this proposition is equivalent to this proposition. And how would I prove this? Well, I already know that one side is true, x equals x. That's by axiom 1. So by axiom 1, x equals x. So x equals x or x equals y. So there I'm using the basic rule for or, by the way, where knowing just phi or psi individually lets me deduce phi or psi. So there I'm using that fact. So I'm going from x equals x to x equals x or something. Okay, so therefore x is in there. Now, can I just skip this stuff? Can I just say x is obviously in there? Definitely not. Maybe later when we've done this a few times, to the point that we're bored of it and it becomes kind of standard for us, then we can skip to just saying x is in here. But this is like literally one of the first times we ever use the definition of doubleton. If even the first time we ever have a need to use the definition for doubleton, we skip using it, then something is wrong. Then how can we know if we even chose a working definition if we never use it? So we are still at the stage where we should be using all of our definitions. Notice, however, that I did not mention that I used axiom 5. That's okay for now. So I just skipped to this gives this without directly mentioning exactly how I used axiom 5. Okay, and also notice that this took some thinking to prove that x is an element of the doubleton xy. Like, I couldn't just get this just from looking at the notation. Like, look, it's right here. X is right here inside the physical appearance of the notation. Therefore, x is in there. No, that's not sufficient. The notation is arbitrarily chosen. I could have chosen a different notation that does not make it look like it's physically in there, like the symbol is physically in there. And besides, that's not what the membership symbol means. It doesn't mean something about how the notation is physically arranged. No, the membership symbol does nothing other than what axiom 5 allows it to do. That is all the membership symbol does. And because axiom 5 only gives you a way of working with sets when they're defined using this notation, variable bar proposition, where you have this condition for membership, because of that, you need to have the original definition of something written in this form, variable bar and then condition for membership, in order to make any use of membership, of a membership statement. Okay, so coming back here, I've got x is in there, right? But this is equal to this, right? Axiom 2 says if you take any proposition and replace an object of your choice with something that it's equal to, then that will also be a true proposition. Or then the propositions will be equivalent. So this will be equivalent to X is in there, doubleton UV. Okay, now to make any use of this, I need to break it down, again, using axiom 5. That's the only way to use membership. So axiom 5 says, X satisfies the membership condition of being in doubleton UV. What's the membership condition? Is that you have to either be U or you have to be V. So what I'm using is this proposition. This is the membership condition. So by axiom 5, which I don't need to say that. I've been sort of leaving those words out. So X is either U or X is V. And let me write that in words. Okay, now we have something to drive a proof by cases. My ultimate goal is to prove either this side here or this side. If X is U, then I think maybe I have a shot at proving this side. Maybe I can prove that Y is V. Maybe. If X is V, then maybe I have a shot at proving this side. So now I've got an OR, and I can use it. And that's what proof by cases enables. Okay, case 1, suppose that X is U. Now you might think, how about I do the same thing for Y? I can easily prove that Y is in the doubleton XY, and so Y is in the doubleton UV, and so Y is either U or Y is V. And then I can split into further subcases. Case 1.1, Y is U. Case 1.2, Y is V. Then in case 1.2, we would be done, right? Because we'd have X is U and Y is V. But what would we do in case 1.1, where X is U and Y is U? What would we do in that situation? It feels like we'd have to find some way to split into further cases, or find some other thing to give us some juice to move forward. So this is actually not such a good option to try to focus on Y. If you fiddle with it a bit, then it seems that if you... so what's the goal? At this point, let's focus on the goal. We want to prove that Y is V, specifically. We think that we can prove this side, specifically, rather than this side. So our goal is now to prove Y is V. How about, instead of focusing on the Y part of it, we focus on the V part of it? Because if you focus on the Y part of it, if you just start with, Y is in UV, and then so Y is U or Y is V, that doesn't tell you necessarily that Y is V. You get stuck in this Y is U case. But why do we think that Y has to be V? Well, we think that because it feels like somebody has to be V. Between X and Y, at least one of them has to be V. Because V is in here, and therefore it's in here. That's the idea. So focus on the fact that V is in here, and therefore in here. So let me make this argument, but now faster. Since V equals V, we have V equals U or V equals V. So V must be in the doubleton UV using the membership condition for doubleton UV. So using this idea here again. Therefore, by axiom 2, since this is equal to this, we have that. So v equals x or v equals y, using axiom 5 again to break down what this is saying. Now, how is this any better than what I was mentioning before? I mean, if v is y, then we're done, because it seems we've proven this side of things. But what if v is x? Well, now it looks kind of interesting. What happens when v is x? If v is x, then it looks like we end up with v equals u. If v is x, then it looks like v ends up being the same as u. And yeah, then the right-hand side becomes a doubleton in which we have the two things being equal. But if you look at the previous theorem, so we're currently working on proving Theorem 23, that means Theorem 22 is available. By the time you reach Theorem 23, Theorem 22 can be assumed to be already proven. That's why when you're doing your homework and you're doing Theorem 22, you would not be allowed to use Theorem 23, because that would possibly make things circular. So Theorem 22 tells us about what happens to a doubleton when the two components of it are equal. And, you know, I'm seeing now that maybe if instead of focusing on v, you know, I said earlier when we're trying to prove this equality, let's focus on the fact that somebody in here is v rather than focusing on the fact that somebody in here is y. I think either way we would have ended up at a similar place. So maybe it does not matter that we focused on the v rather than focusing on the y. Anyway, yeah, so this will lead to another case split. So case 1.1, suppose v is x, and then case 1.2, suppose v is y. And just so I don't forget what the original case split above was about, it was about whether x is u or x is v. So case 1 was x is u. Let me fill in. Case 2, suppose that x is v. So I recommend that when you're typing up your proof, it does not work so well on paper, but digitally it works well. When you write cases, write both so that you remember to cover them both, and then fill them in after. So I should have written both. Okay, and digitally that's fine because I can just move these up and down to make more room if I need it. Okay, so in the case v equals x, I'm not immediately done. But if v equals y, then I'm done, right? Because then I've proven x equals u and y equals v, which is one side of the either or that I need to prove. So let me end the easy branch here. If v equals y, then x equals u and y equals v. So we have x equals u and y equals v, or x equals v and y equals u. We have this or because we have the left side of it. Remember, our goal is to reach victory in every case. So here we have reached victory. This is what we are trying to prove. X equals u and y equals v, or x equals v and y equals u. I've just written it symbolically here, is all. Okay, so case 1.2 is done. We hope that we end up with all cases being done. Case 1.1, let's see. So if v is x, then we are in a situation where, let's see, in case 1, x is u. If v is x, then u equals v, right? So that means that the doubleton uv that we were looking at here was not really a doubleton. If u equals v, then according to Theorem 22, just replace the x's by u's, replace the y's by v's, and replace the u's by something else. This is saying that the doubleton is actually just a singleton, where what you can put here is just equal to either one of the two things in your doubleton. So according to Theorem 22, since u equals v, by theorem 22, the doubleton uv, since u equals v, is just singleton u. Okay, so then our original assumption up here is that doubleton xy equals singleton u. So our original assumption is this. Not really, our original assumption is this, but it's very close to this. It's just one axiom 2 usage away. This, but then replace doubleton uv by something that we are now saying it's equal to, which is singleton u. Okay, this is again another one of these theorem 22 situations, where we have a doubleton actually being a singleton. Except we're using it in the other direction now. So we're using theorem 22 again. Excuse me, but notice the direction. So theorem 22 is an if and only if. Up here, we had a doubleton where we have one thing, where we have both of the things inside the doubleton being equal. So we had this side, except with u and v rather than x and y. And so we were using the arrow that goes this way, from the right to the left, and deducing that since u equals v, we deduce that the doubleton of uv equals the singleton of, and then either one of them. Now we're going to use theorem 22 in the other direction. Now we have that a certain doubleton equals a certain singleton. So we're going to go from the left, we have something more like the left. Actually, this time you don't have to do any variable replacements. We have literally with the same variables, x, y, and u. We have that left side there. And then we're going to go make a deduction from the left to the right. So this is the power of an if and only if, is you can use it in both directions. So now we're going to conclude that from here, we're going to conclude that x and y and u are all the same thing. X equals y equals u. Okay, I made some extra room there. So how does this help? So my goal is to prove, I guess, that y equals v, right? But I'm in a subcase where x is v, and I've proven that y is x. So if y is x and x is v, then we have y is v, and so we're finished. So let me write that kind of in an order that shows exactly why it's true. So since y equals x, so that's applying the symmetry of equality to this equality. Since y equals x and x equals v, that's this equality, but again, symmetry used to flip it around. We have y equals v. So you see how I wrote down y equals v by first writing down two individual equalities that you can look back in the proof and find them. So this is kind of nice to the reader to do this rather than just saying, therefore we have y equals v. No, instead you start from y and then work your way towards v in such a way that each individual equality you write down can actually be found as already established somewhere in the proof. Okay, then we are done. So now I can just basically say the same stuff that I said here. Then x equals u and y equals v. So either x equals u and y equals v or whatever. And that's what I want to reach. This is the conclusion I want to reach at the end of every case. So that's it for case 1.1. Now case 2, suppose x is v. So now we're clearing all other assumptions except for the initial assumption and what we figured out up here. Clear all these other case assumptions, and now suppose x equals v. So what can we do now? So probably what we're going to do is try to prove this side rather than trying to prove this side of the OR. And you might just try to do the same thing. So you might just go ahead and try to repeat the argument here, but basically with u and v swapped. So same argument, but with u and v swapped. And you could do that. In fact, it's very easy to do in LaTeX if you're typing. You would just take a bunch of stuff here and copy and paste it, like all of this stuff here. Copy and paste it and then swap two variables. By the way, be super careful when you do that. It's very easy to forget to switch things up after you copy and paste. Okay, but that's not so elegant. There is actually a nicer way to try to cut down the length of the proof, which is, rather than making our case split be based on whether x is u or x is v, we can make our case split be based on whether x is u at all. Okay, so the reason I suggest that is that when you're doing case 2, so let's imagine I'm not copying and pasting, I'm just straight up writing it. So I say, since, oh, by the way, case 1 is done, so I can put a check mark here, since we finished all subcases inside case 1. Yeah, so if I'm just straight up doing it this way, just copying what's up here, swapping u and v, then I would say, let's see, let me write it kind of more scratchy. So I would focus on the fact that maybe u is in xy. So that would tell me that u is x or u is y. And then I would have two cases to deal with. In the case where u is y, I would be done because I would have the right side here. X is v and u is y. But in the case where u is x, I would have some more work to do. And that would be like case 1.1, the case where u is x, where it was more work. But doesn't that feel silly that we'd have to do that? That we'd have to deal with a special subcase of case 2 where u is x? That feels silly considering that case 1 already covered the possibility that u is x. So that just seems like it should not be needed. Well, you could always say, like, yeah, look above, we already covered the case u is x. It was case 1. But actually what this is suggesting is that if we just focus on whether or not u is x, then we might get a cleaner case split. So the way I think about it is, this case split is focusing on the possibility that u is x or the possibility that x is v. That's how it's currently organized. But it could be that x is both, right? So when I go to case 2 and I say suppose x is v, I'm not also supposing that x isn't u. It could also be u, right? If I'm in one of these more complicated cases. On the other hand, if I base my case split instead of on this fact that either x is u or x is v, if I instead base it on, okay, either x is u or it isn't u, then my cases are stronger. My case assumptions give me more to work with. So let me arrange it that way. So what I'll do here is, instead of focusing on this, I mean, it's true, but let me not base my case split on it. So let me just say, by excluded middle, either x equals u or x is not equal to u. For any statement, it's either true or it's false. So case 1, suppose that x equals u, then we can do that. Then case 2, suppose x, instead of x equals v, suppose x is not equal to u. This is giving me something stronger to work with. And I say it's stronger because I still know that either x equals u or x equals v. So let me, I think I don't make any use of this fact up here. So let me point it out down there. Or let's see. So one thing I can do is rearrange a bit. Okay, so I made some room here, and I'm just gonna move this down so that it's on its own line and centered. And what I can do when I do this is give it a label. Like, I can call it 1. So this statement here becomes a display with a number. It's display number 1. So now I can refer to it later, because I don't use this in case 1. And I'm not even using it for the case split. Now the case split is based on x is u or x is not u. But now I can use this deduction, which took some effort, and we still want to eventually use it. I can use it later on and easily refer back to it. So I'll show you in a moment how you would do this kind of thing in LaTeX. It's really very useful. Okay, so suppose x is not u. Well, by 1, I probably could have just moved the entire argument 1 down to here, but I just kind of want to show you how you would do things this way. This is also helpful if you need to use that same statement up there in multiple locations later on. So by 1, we have, okay, so why am I focusing on 1? Because I'm assuming x is not u. If I have x is u, if I have x is u or x is v, and I know x is not u in case 2, x is u or x is v, and x is not u, then x must be v, right? This is one of our derived rules, number 12 here. Alternative eliminated. If you know phi or psi, and you know not phi, then you know it must be that psi. We know x is u or x is v, and we know x is not u. So by 1 we have x is v. So I still got the x is v that I had earlier crossed off, but now I additionally have x is not u. That's why this case is more, splitting the cases this way makes the case assumption more powerful. So now we have x is v. Now my goal is to prove that y is u, right? Because I think I'm in a situation where I can prove this right side of the OR here, x is v and y is u. So my goal is to prove that y is u. So I could start by focusing on the fact that y is in there, and therefore y is in there. So either y is u or y is v. Then if y is u, then I'm done, and if y is v, then I'm in another complicated case. But here's a way in which case 2 helps. Or rather, here's a way in which the new and improved red version of case 2 helps. If I, instead of focusing on y, I focus on u, and I go, well, u is either x or y. Well, first you say u is definitely in here, and here is equal to here. So u is either x or y. Then one of the two in the OR that we end up with has already been eliminated. That x is u. We know u is not x, so we immediately know that u must be y. And then we would be finished with no further case split. So focus on u. Okay, let's clean that up and write it up. So since u equals u, we have u equals u or u equals v. So by axiom 5, u is in there. Since it's been a while since we mentioned this equality, so it may be good to remind the reader of it. Since these are equal, we have then that u is in there. Just replacing this by something that's equal to it. therefore, using axiom 5, which is the only way I can make any use of this, we have u is x or u is y. But u is not x. So this is, again, alternative eliminated. Since u is definitely not x, we have that u is y. Thus, x is v. So let me find the things that I needed. We got x is v, and we got u is y. X is v, and let me write it as y is u. So we reached this or. I can just copy and paste this, actually. We reached the same or that we need to reach here. Because we got this right side of it. And that's enough to prove the or. So then case 2 is finished. And we are done with the proof. Okay, one more thing I want to show you in this video is how to do this referencing thing, where you label a certain display so that you can then reference it later. Of course, you can just stick a number there and then use the number later, but there's a much nicer way. Okay, so here's an example. Let's say I'm trying to write a proof with a display that has a label, and I want to label it so that I can reference something later in the proof. Then, well, you've seen how to write something centered. You can use double dollar signs. At least I think I have shown you that before. Yeah, I have. So I could write something like this, like that, just sticking it in double dollar signs, and maybe putting some words like we have colon this and then a period, like that. So we have, and then here it is on display. Now how do I get a number to refer to it later? So instead of using double dollar signs like this, you can put it in an equation environment. So put it between begin equation and end equation. And I don't need the dollar signs anymore. Once you are between begin and end equation, you're already in math mode. Meaning it's as though you're between dollar signs, and everything you write is interpreted as math. Then it gives me the number. So you get a number, and it'll automatically increment that number every time you create a new one of these equations. Then if you want to later refer to the number, you need to include a label here. So anywhere in between the equation, anywhere inside the equation environment, you can do this label command and then give the label a name. So it doesn't matter what you call it. If you have a long document, you probably want to organize it nicely and give the things memorable names. But how about I just call this fun display. And then later I do a bunch of talking like this, and then by that time maybe I've talked so much that the reader has already forgotten about display 1 here, so I want to refer to it. So I want to say by, and then I'm not going to type 1 because that number can change as I change my document. Instead, to reference the label, you do ref, this ref command, and then the name of the label, which I called fun display. We have blah. So now if I compile that, you can see it says by 1. Sorry, there I've zoomed in. It says by 1 we have blah, where 1 refers to the thing labeled 1. It's not very nice that it has parentheses here and not here. So you should actually stick parentheses around it, like that. So by 1 we have whatever. Okay, so that's a nice way to establish something, a statement somewhere in your proof, and then go back and refer to it later.